Yeah, I can see that now, mate.
Yeah, excellent. Okay, so yeah, thanks for the introduction, Tony, and thank you everyone for inviting me today. I'll just give a bit of a caveat that I woke up with a stinking cold after being off on leave with the kids, so I'll do my best. If you're struggling to understand my thick Derby accent as well as a cold, then I'll yeah, please just give us a shout, and I'll try to reiterate what I've been trying to say. So yeah, I'm going to give you a bit of a talk around some of the rough ride work that we've been doing as Network Rail, and more specifically looking at the vehicle response side of things. And hopefully we can perhaps challenge everyone on the call to know a bit more about rough rides as well, and challenge what you think you know about rough rides potentially. So just a bit of an overview of the presentation then. I've just given a brief background into myself, what's brought me into the space of rough rides, and then I'll probably go through what we actually mean by the term rough ride, and I'll touch on why it's an issue, and then give a brief sort of overview of track geometry recording process, specifically the ride quality metric we derive from track geometry, and discuss what we think we know, I guess is more to the point. Next, I'll give an overview of the work we've done to monitor vehicle response, as I just mentioned, and perhaps give some context as well into the simulation work that we've done separately to that. And finally, I'll just give a bit of a summary of the learning from the most recent work that we've done, and before moving on to a bit of a Q&A. So hopefully it'll give you good insight. Okay, so a bit about myself then. So quick canter through I've perhaps ended up leading a lot of the rough ride work. So I started my career nearly over 20 years ago, 22 years ago, at Serco Rail Test as a technical apprentice. I spent most of the time at Serco doing vehicle testing, so compliance, so ride compliance, as well as sort of general vehicle safety, safety compliance as well. And yeah, one of the sort of key moments that I can remember was physically ride testing the Pendolinos at 140 mile an hour down West Coast Main Line. And yeah, as a young sort of 17-year-old lad, I thought this is never going to work. We're all going to crash, and fortunately we didn't. It was quite a successful test. But obviously, yeah, from a safety case perspective, it never got taken forward. But yeah, there's a bit of an image on the slide. So although it's Network Rail 2001, not quite sure why I had the Network Rail pass, because it was definitely Serco. But obviously I've not aged one bit in those 22 years. So I then moved over to Network Rail in 2005 and took after the testing of the infrastructure, so effectively looking down rather than looking up. And I worked on the new measurement train and all over the infrastructure monitoring vehicles, but predominantly sort of track geometry testing. And then in sort of 2012, Network Rail established the quadrant in Milton Keynes, and moved the data processing of the infrastructure monitoring vehicles down to Milton Keynes. So I supported that setup of the new geometry processing team, and quite enjoyed it actually. It was completely different to the engineering that I've been doing in the past. And then a bit of direction change a few years later, went over to LMW Route, to support the implementation of like PLPR as an example, so plain line pattern recognition, as well as some other sort of big change programs, things like RBM, click roster, things like that. And yeah, again, it was a move away from engineering, but it was really enjoyable to understand how the structure of the sort of route at the time worked. But then the role came back up in what we call the mobile monitoring team, and that's the team where you have sort of hands-on experience with the specification and fitment of measurement systems on our infrastructure monitoring fleet, sorry, and other rolling stock as well. So we did look at some operators' vehicles in that time. And then, yeah, I led the team for a year or so during COVID. That was really challenging, and also went through the restructure of the Network Rail for Point Passage's first programme. So, yeah, the team sort of moved from under the safety technical engineering sort of banner that we were under into asset information services. And then I sort of realised that I didn't have a broad or enough sort of information, enough detail. So a bit of a development opportunity came up to look in the track team within Network Rail. So I moved over there, and then yeah, that's where I am now finally. So just currently looking after the European Intertrack 3 work stream, and perhaps throughout all those roles, I've been working very much with the sort of instrumentation, testing, R&D. Across sort of track geometry and vehicle engineering. So perhaps a good sort of broad grounding really for that vehicle response work. Okay, so moving on to rough rides then, and what do we mean by rough rides? And perhaps what do we mean in Network Rail by driver reported rough rides? That's a phrase that's sort of been used quite frequently of late. So if we pull reports from our fault management systems, there's many terms that could be used or could be considered as a rough ride. So terms things like felt a lurch or a bad bump or kick, jolt, dip in the track, bottomed out, lots of different terminology out there. And on the screen, we can see a BS standard, so BS 12299, and that provides a useful definition actually, because it's a standard specifically designed to offer guidance on the measurement and evaluation of passenger ride comfort. So there's a lot of text on that slide, I do acknowledge that, but just to pull out two main sort of parts from that. So the first part is like ride comfort. So yeah, there's a bit of narrative there to discuss that ride comfort refers to like an average comfort over 5 minutes. And we manage that already by looking at track geometry, standard deviation metrics, or track quality, depending on how you phrase it. And I'll talk about that a little bit later on. But in addition to the track geometry, there's also the design element as well. So yeah, we've got standards that limit or allow acceptable levels of sort of cant efficiency, as an example. And again, I'll talk about that later on. So the second part then is section 5.5C, and that details a sort of instantaneous sensation or sudden change in average sensation. So i.e. the sort of, change of mean lateral acceleration with possible oscillation or roll or motion, or even jerk, which is rate of change of acceleration. So again, that gives us a good definition of, a lateral movement that you sense sort of as a one-off transient event. But what it doesn't define is the same element or same response vertically. So we've sort of used it as a broad term, and therefore our sort of definition is a driver report rough ride is that sort of sudden, instantaneous, probably unacceptable vehicle response to track condition. So that's a sort of definition that we've applied to the work that we're doing. So slightly separate to the average comfort factor. Okay, so why is it an issue then? Well, apart from the obvious, passenger comfort and passenger satisfaction, a significant issue is safety. So the reporting of rough rides is sort of one of the last means of control of our prevention of derailment risk very high, which can be seen at the top image. So we can see that we've got the green arrow on the left-hand side of the top image is our track geometry measurement means of control. So obviously we measure track geometry at a set frequency. And then further towards the right, we can see sort of the second to last event really before where we consider an issue is that rough ride reporting instance. And the reason that we do that is, the unacceptable poor response could be a result of a broken rail, for example. And that's why, we do get drivers and train crew reporting those issues. However, looking through our statistics, many of the rough rides, we cannot see anything wrong. So in fact, what we've understood is over 60% that was reported on LNW, so West Coast South, in 2017, nothing at all could be found wrong with the track asset. So it was within all of our tolerances. So no alert limit faults, no intervention limit faults, no poor track quality. So the significant issue we face isn't necessarily safety, but the impact on performance and obviously asset availability that goes with that. So when a rough ride is reported, typically the signaller will block the line whilst the PWA team are sent to investigate, and that process is sort of mapped on the right-hand side. Appreciate it's difficult to see, but it starts accumulating. It starts accumulating delay minutes, and obviously until the line is inspected and declared fit for the passage of trains, or it's declared that there is actually an issue, and we have a put speed restriction, remedial works planned, etc., etc. The bottom chart it comes kindly from the TMA at Rugby in around 2018, and it shows so the top sort of line on the right hand side, we can see that the maximum Schedule 8 equating to bump reports was just under 7 million in delay minutes, and that's for financial year 16-17. So if you think the 60% of no fault found that I mentioned earlier, that's well over 3 million, knocking on or £4 million in delay minutes, and that's just on West Coast South. So it's a significant issue when it comes to cost avoidance. Okay, so as we mentioned, then we try and manage it and manage the average ride comfort by our track quality metrics and track design limitations. So TRK 001 on the right hand side is one of the network rail standards, and it details our track geometry inspection and minimum actions. It also provides like a framework for the inspection of geometry, as I mentioned before, and the sort of frequencies, and provides limits, actions, the twist gauge, etc., etc. And to manage that ride comfort or passenger comfort, we essentially infer comfort from our standard deviation metric or track quality metric, which is the standard deviation over the vertical profile and lateral profile over each eighth of a mile of the network. So in essence, the higher the standard deviation, the more variability there is in that vertical profile or lateral profile, and therefore the assumed more uncomfortable eighth. So the table on the right, just behind the CCQ chart, is essentially taken from TRK 001, and it plots nominal sort of speed ranges, line speed ranges, a standard deviation figure, and then we can align that to a track quality banding. So good, satisfactory, poor, very poor, or maximum band, or super red, as it's otherwise known. And then the chart in front of that is, our color-coded quality chart or CCQ chart. So this is essentially every eighth of a mile done a section of track for every single recording. And what we can see here is, you can see, we've had significantly poor area or poor couple of eighths. Some remedial work would have been done and it improves. So that's how we currently manage it. If the SD figure falls within the maximum band, also known as super, as I mentioned, typically speed restrictions will be applied and maintenance carried out to reduce the risk of that poor ride quality. So essentially slowing the train down, which potentially increases the comfort by moving it effectively down the bands. So I won't dwell on that too much, but we'll talk about it a bit later on. And just to sort of draw out then, the metrics are over different wavelengths. So we've got our worst top over 35 meters, which is the worst of the left and right rails, mean top, which is the average of both rails, over 70 meters. Then we've got the mean alignment over 35 meters and mean alignment over 70 meters. And those are quite significant values, the wavelengths. I'll sort of talk about that in a moment. So obviously, before we even get to recording geometry and managing it from geometry, there's the design geometry. So obviously, by introducing or setting limiting factors within our track design handbook, we can, especially or specifically things like cant efficiency, it allows us to control that quasi-static sort of lateral force. So rather than being sort of thrown to the side as we go around the corner, we can apply the force. So it's obviously going more vertically into the asset. So again, I won't dwell on that too much. Because there was a fantastic article actually written by Andy Steele in volume 140, so 140 of the PDY journal. So really recommend that you go and see that. And that's where I borrowed a couple of these images from as well. Okay, so why do we measure top and alignment then at 35 and 70 meters? So it all comes back essentially to the way that passengers respond to acceleration, and that in itself is really complex. So I won't go into it in too much detail, but essentially the first sort of diagram shows that initial basic relationship. So effectively we have geometry and geometry variation, and that transfers through the primary, secondary suspension into the car body, and then it's felt by the passenger. So the transmission of energy through the vehicle is obviously filtered and damped by the suspension before reaching the passenger. And what we understand is that standard sort of human response is quite well documented. And what we can see in the second chart at the top is effectively that humans have a high sensitivity to frequencies of around 5 to 16 hertz in the vertical plane, but much lower, so 0.6 to 2 hertz in the lateral or horizontal movement. Just one thing to note as well is that other than visually, if you're going at a constant velocity, it can't be perceived. So it's only when there's a sudden change or a change that you notice that. So that obviously relates to the frequency element as well. And what we can do then is by understanding the sort of vehicle and bogie and suspension responses, we can use that and use what we understand from the person weighting or the human perception weighting to effectively change from a temporal sort of measurement into a distance measurement. So effectively understanding the effective displacement on the person. So by applying sort of and understanding filter cutoffs in the data and looking at the bottom plot, it was understood that high-speed vehicles with sort of bogey responses of around 0.9 hertz through that filtering process, running at sort of 200 kilometers an hour, so 125, has a corresponding wavelength of around 70 meters that falls within that susceptibility to passenger comfort. And similarly with sort of more suburban stock that have stiffer suspension but run at a slower speed, the sort of bogey and vehicle response is more around 1.6 hertz. So again, that led to that sort of crossover at around 32 hertz. So that's effectively why we pick 35 and 70 meters, because it's based on the perceived comfort for passengers of like Sprinter stock and HSTs from some sort of 30 to 40 years ago. Okay, so a bit of project history. So knowing obviously what we know and the way we manage it, why are we still getting rough rides then? And why are we starting to look in more detail? So we'll start in perhaps early 2000s really, where we saw the introduction of the Pendolinos on West Coast. And yeah, this is, as we know, it's an enhanced permissible speed section. And as I mentioned earlier, it was originally designed for sort of 140 mile an hour running, but it wasn't followed through because of the safety case, as I understand. But the introduction saw like a significant increase in bumps, and the West Coast has been like heavily remodeled as well, renewed. So you know, you'd argue it was the best sort of track condition that we had at the time. So sort of Alstom, Virgin Trains West Coast at the time, and Network Rail all sort of collaborated to investigate. And the outcome saw essentially a significant increase in damping rates across the fleet. So I think the primary suspension was increased by around 200%, and the secondary suspension increased by 300%. So quite significant changes. And it seemed to largely solve the issue, but we did sort of see thereafter, you know, small reports of random or sporadic rough rides thereafter. But sort of fast forward 10 years, and there was almost like a steady increase in rough ride reports again. So this time, Dr. Burstow, that many people may know, and Dr. Sinsin Su, who's now regional engineer in Easton, performed some simulation work. And they understood that over long wavelength variations, so talking around 120 meter wavelengths, with variations in top profile around 40 millimeters peak to peak, they were seeing bump stop contact. And also with some smaller variations in peak magnitude over shorter wavelengths that contributed to that bump stop contact as well when we saw those longer wavelength features. But as part of that work, it was understood and recommended that they instrumented some vehicles to start detecting this bump stop contact and essentially peak acceleration, so they could develop limits and try and prevent it from, understand it and prevent it from happening. So again, fast forward a few more years, this time about 2018, and what did we learn from the recommendations from the previous work? So firstly then, that the instrumentation of a number of Pendolinos did happen, and we installed 7 bump boxes across a number of vehicles. What we understood though is that those outputs, so those acceleration outputs, didn't correlate with track faults. So they didn't correlate where we had a track geometry fault. They didn't correlate where we had any poor track quality issues either. And finally, they didn't correlate where we had any rough rides. So we were getting high accelerations, but we couldn't understand why or what the risk was essentially. So again, we kind of saw that increase in rough rides throughout that time period again. So Alstom approached Network Rail to see if we could collaborate and bring in additional data. So essentially they were monitoring their fleets, and they've got sort of bogey measurement devices. So they're suggesting that if we correlate that with our measured data, could we start to see that correlation effectively and try and understand what the issue was. So in addition, we instrumented a number of vehicles as well to further that work, so move away from just sort of peak acceleration. And this is where the term driver reported rough ride kind of originated. So again, looping back to that sort of discrete, instantaneous poor response that I mentioned earlier. So we work with 4 main suppliers, in addition with Virgin Trains and Alstom. And we picked a number of case study sites where we're seeing sort of poor response or measured poor response, just to see if we could predict it. And what we did was we used the sort of learning to try and put together a almost like a prediction. So if we can start to measure it, can we use that as a signature to then apply to other parts of the network to see if we can see and effectively prevent or try and find out where we're going to get issues in future. So we called that a bit of a blind test and set the suppliers off to see if they could do that. But again, we kind of find that again the locations were not correlating with where we had geometry faults, not correlating with track quality, and the peak accelerations weren't. You couldn't really give it a signature because they were different in all the different cases. So what the supplier started to do though was understand different vehicle specific dynamics that were affecting some of the outputs, and they started to apply certain filtering, and we did start to see some benefit in doing so, but the project sort of ended. And a good sort of example of what we found was there was during a high-speed curve, we identified a number of rail defects, so ultrasonic defects. The defects were removed by spot rail replacements rather than re-railing the whole curve with brand new rail sections. But on the existing rail sections, we had headwear, quite significant headwear actually, and the team were unable to fully blend the new section in with the existing section. So as the train obviously traversed around the curve, high cant, high speed, we're effectively seeing the bogie hunting around these sections of new rail. So we couldn't really see anything significant in the geometry, but we saw it quite predominantly in the data output from the vehicle. So again, it allowed us to then start to change the way we were looking at some of the data. And then we put together some recommendations off the back of that. And those recommendations were essentially further testing and development of the algorithms that we started to put together, and also to try and better understand the vehicle response side. So could we do some simulation work as well to understand what different rolling stock types see with different sort of input track conditions. So yeah, just before 2020 then, we started two main work streams off the back of the recommendations from the previous work. So one was we set a design contest to widen the physical trials to open the market up essentially to more suppliers to see if we can start to improve the capability of in-service monitoring. But then also we looked at collaborating with other industry partners as well, so people like ProRail, Ricardo, to look at more simulation element. So the actual fitment of the vehicle was really good and really useful because we were able to again collaborate further with people like ScotRail and Porterbrook as a leasing company and an operator to allow a more coordinated sort of installation approach. So just a bit of history on the simulation. The simulation exercise effectively takes a variety of rolling stock models and applies those to measure geometry, and then that outputs the vehicle response, that track input. So for the simulation, we actually gave Ricardo multiple sort of measurements of our track geometry, and then they picked some generic rolling stock types that are quite pertinent to the rolling stock that we've got in the UK, and then give us the output of that. And yeah, straight away we had poor response over areas where we had no immediate geometry issues, and we had okay vehicle response where we did have intervention limit faults. So kind of not quite what we expected, but sort of validated some of the work that we'd seen previous. So again, I mean, it can be sort of simply explained if you look at the top left chart, where the diagram effectively shows that we've got multiple variations in like a waveform, which are fundamentally different, but they have an equal peak magnitude. So say we have a 10mm peak magnitude in all of them, the actual waveforms are completely different, and that kind of makes sense. You're going to see a different response to those. But what we understand more so is that not only will the vehicles see those different waveforms differently, but different vehicles will respond differently to them as well. And again, it doesn't sound it sounds quite obvious when you say it out loud, but we perhaps don't manage that well enough currently within our current controls. So also what we found was that we understand that velocity is obviously a major factor and can be an issue, but there's also a case to suggest that for given poor response, we can see and use this information to see where velocity and where at a certain velocity we start to see that significant poor response. So the chart on the sort of bottom left is identifying an area of poor response, and the bottom right chart is sort of speed increments. So we can see what the vehicle's response is at sort of 20 kilometers an hour, 30, 40, 50, etc. And we can see at 80 kilometers an hour is where it starts to peak. The vehicle response starts to peak above an unacceptable level, for want of a better phrase. So maybe we could use this to sort of impose a speed restriction and limit the amount of delay rather than stop traffic, etc., etc. So that's something that we're keen to sort of progress in future. So we think it's a really useful approach, and this is something that's currently in place in ProRail in the Netherlands. And looking back sort of on the conception of the new measurement train, the AEA technology did look at implementing something called Vampire Live, which was effectively doing something similar, using the live geometry data from NMT to model the simulation of vehicles, but it never really took off. But I think there's definitely opportunity to look at it in the future. Okay, so moving over to the second part of the recommendation, which was furthering the trial. So again, we looked at more monitoring equipment installations, and here's just a few images of the types of equipment that we had fitted from the different suppliers. It's sort of, I'll make a note that the different suppliers have got different technology across different parts of the vehicle. So it wasn't a direct correlation between one supplier to the next. It was for us to better understand, what types of technology and whereabouts on the vehicle can we start to see significant issues. And also, if we can measure, obviously, at track level, primary suspension, secondary suspension, car body, we can get a good understanding of what's happening through that system on different rolling stock. So we can see on sort of the far top right image, we've got axle level accelerometers. We've got things, so the sort of top center image, instrumentation on the floor of the cab. The bottom right, we've got instrumentation on the bogie, so above primary suspension. On the sort of center left, we've got things above sort of head height. So again, trying to get that broad spread. And then finally, the sort of top left image is just a bit of a schematic on one of the approaches from Deutsche Bahn on how they sort of integrated the measurement system with data transfer and that sort of stuff. Other than one of the suppliers that looked at sort of more visual, so using forward-facing video and looking at the displacement of the rails against a fixed video, most of them used sort of 3 to 6 degrees of freedom systems, so essentially accelerometers or gyroscope based or a combination of the two. Okay, but the sort of fitment of the implementation, the instrumentation is only the sort of, it's probably the easy bit if we're honest. The main sort of challenge is the data processing, filtering, and obviously the management of that data. So this slide just gives a bit of an overview, and I appreciate this is a busy slide as well. Just gives a look at the development of the sort of rough ride predictor algorithm. So I mentioned earlier that we're trying to predict where we're going to get these issues, looking at essentially known events of past and being able to predict where we're going to see them in future. And so this is like the next step to that. And I think one of the main sort of things to pull out is that the first chart on the left-hand side is a plot where we actually recorded through a rough ride. So it's a vehicle that we fitted that subsequently had a rough ride report, and we had data before, actually on the day of the rough ride report, the rough ride itself, and then after. So the red line is the actual report, the time and day that the vehicle reported that rough ride. But what we can see behind it, appreciate it's probably not very clear, is lots of sort of darker graphs that show higher amplitude, and that higher amplitude was before and after the report. So effectively what it's showing is the subjectiveness, if you like, of the reports in the first place from the driver or train crew. The suppliers understand that, but what they've done is try to learn and try to model that to develop the sort of prediction algorithms. So what we can see, like the bottom left, is using sort of multiple peaks. They're basically generating a bit of almost like a risk score to then be able to identify certain sites. So not just seeing one filtered element, but multiple filtered elements at set frequencies, things like that. And then the sort of top right and sort of center plots, we can start to see some basic degradation based on those risk scorers and everything else that we've learned to try and give that prediction element. And then finally, the bottom right just shows a direct output from the BS 12299 that I mentioned earlier. And again, this needs a little bit of work because we understand that this doesn't necessarily correlate directly with where we think we've got poor ride issues either. So I think it's telling us something that's important, but we need to do some more analysis on that. Okay, so some of the results, and I appreciate this slide's not very clear either, but because the suppliers have different sort of various maturity levels against the sort of problem statement, the successes sort of varied as well. But I think something that's again important to sort of draw out is that one of our suppliers accurately predicted 6 out of 12 rough rides before they occurred. So I think that 50% prediction, and the time that they gave for that prediction was quite significant. So a couple of months in some cases. So I think that's definitely a benefit. And the log of what they provided to us is on the right. So again, difficult to read, difficult to see, but essentially they gave us some location information and some narrative as to what was going off, and we monitored it. And came rough riding in a lot of cases. Some are still outstanding because it's very recent data. The second supply wasn't as successful percentage-wise, but still managed to identify 2 out of 15. So they provided 15, two were actually rough rides. The supplier at the top of the screen, so they found that by setting different thresholds, they can get to a usable figure in the sense of they're able to provide or accurately predict 5 out of 7, but you start changing that sort of threshold and it reduces the number of false positives, but then it also reduces the number of, or the percentage of accuracy match, if you like. So some work to do around that. And then the tables at the bottom, that was focusing specifically on the ride comfort, so BS 12299. And again, the percentage match against known rough rides was really low. So we're talking sort of 5%, 14% across 2 different fleet types. But all the green sort of boxes, that's where we had matches against known rough rides, where we saw significant response rates as well at set frequencies. So again, there's certain things to learn from that, especially with the vehicle movement side. So again, quite successful in all regards. But so moving on to additional learning. So what do we know, and what have we learned from the sort of trials then? So I think one of the main things is that not all rough rides are the same. So they're all different. And this sort of talk around getting a signature was quite naive, way back when we sort of came up with this sort of solution or scenario, because there's all the different 6 degrees of freedom all influence how that movement happens, how that response happens on the vehicle. And I think something that I've been quite clear on and trying to cascade across the industry as well, it's not a track asset issue. So everyone's quick to say your track's poor quality, it's a track's fault. It's not, it's a system issue. And this is what we're seeing, the way we currently manage the track asset doesn't necessarily relate to how we manage that system and system interface. Excuse me. So we also know that sort of predicting rough rides is complicated. There's so many variables, so many influences on that response. Things like different types of vehicle that have got different wheelbases, different bogie wheelbases, different suspension characteristics. They're likely to be under different loading conditions, kineticity. So we're going to have wear on the rails. The wheels are likely to have wear, and that's not going to be consistent throughout any point in time across different rolling stock types either. The subjectiveness, as I mentioned before, from the actual reporting. So there's a lot of learning that we've actually got from it. I think something else that I want to draw out, I mentioned sort of velocity earlier, and being able to sort of apply maybe a lower speed restriction to mitigate or manage that sort of delay minute attribution, if you like, or reducing it or minimising it. One thing that we have learned as well is in some cases there's a bit of a Goldilocks sort of velocity, whereby a vehicle going at a certain speed can be adversely affected by the track input, but if it's going faster, it's fine. If it's going slower, it's fine as well. And the sort of top chart on the graph on the slide there shows that. So the sort of peak that we can see is the vehicle response, and there's sort of 4 different lines there. The green line is at, I think, 40 mile per hour, but there's plots there at 20, 60 and 80 that are obviously significantly less. So there's things to learn around that if we've got this optimum speed that the vehicles respond poorly to, we need to understand that. And then the bottom chart as well is just a bit of an example that the different vehicles respond differently, and it's all related to the sort of power spectral density of the vehicle. And in this case, we've got 3 different vehicles going over the same part of the network, and as we can see on the left of the charts, we've got the orange vehicle that's severely adversely affected in the vertical plane, but it's the best performing in the lateral plane, and this is exactly the same point on the track. And then we've got the yellow vehicle that's, it's not the worst vertically, but it's the worst laterally, but it's quite high in both. And then the blue vehicle that's, you'd argue, is not affected at all. So there's lots and lots of things that, influence the potential of a rough ride. And again, this could be 2 different vehicles, one laterally, one vertically at the same point. So really, really difficult. So there's a bit of a conclusion then. So can we predict rough rides? So I'd say partly yes, but there's a definite but on that. And the but is that there's significant variability that we've understood, and it's also evident that we can't predict all events. So from the trials, it's shown that there's potential in sort of monitoring that vehicle response and asset monitoring from in-service vehicles, which gives the potential for more information about the system than we get currently from the IM fleet. But I think what we understand is the challenges are wider than just the technology, and wider than just the capability of being able to detect the rough rides. But we need to think about things like the rollout and the upscaling of how we could potentially push this into the network and the industry. So things like the commercial approach, the data management approach, the business change. There's a lot of things that we still need to understand, and a lot of thought that still needs to go into some of it. I mean, for myself, I'm sort of suggesting that the only way we're going to realise the benefit from, in-service monitoring is a complete change in asset management approach. So, using the data in anger, and I know that sounds far easier said than done, but we've got a current process for managing track geometry twist faults as an example. We know what the risk is, we know how to manage it, and we know how to prevent, mitigate the risk, if you like, by fixing it. With things like vehicle response, because of all these variables, we're still not in a place where we can categorically state what needs to happen, whether that's at the track or the vehicle level. And I think the only way we're going to get there is by essentially furthering trials, so we can start to understand it a bit more. And I think it'll also help us to sort of define or refine those data management sort of issues and commercial arrangements that we don't quite have an answer for yet. And I think a good example of how we've done that in the past is with the overhead line community. So they've taken a PANDAS system, which is effectively looking at the pantograph and wire interaction from a video, and they're using that to understand issues with height, stagger and forces to plan preventive maintenance, and that's away from the current sort of measurement regime that the infrastructure monitoring vehicles provide. So it's an additional sort of layer of data that they're now acting on. I think this could be something similar. In addition to that, I think there's wider benefits to in-service monitoring, especially, that we've not really considered as part of this trial. So the technology is pretty simple, simple stuff. So accelerometers, gyros, it can give us lots and lots of information. So thinking about, can we start to use axle box accelerations as an example to give us corrugation issues around squats or other RCF issues, and load impact or force detection, etc. So I think that'll allow us to explore and essentially look at wider benefit from the implementation of instrumentation. I mentioned the commercial approach before, and I think the responsibilities and accountabilities really needs to be thought about. So it's unlikely that we as Network Rail would have the appetite to go and contract with multiple suppliers to fit to multiple different operators' vehicles, because it just gets really challenging and really difficult with all the different parties. So could an operator or a Roscoe or leasing company offer it as a managed service? But for that to happen, we need to be clear around the specification, what we're asking for. And again, I think we're a little bit away from that, but we're understanding more and more as sort of time goes on. And then finally, there's things like the industry is looking at setting up data lakes to store lots and lots of different source data. So again, rather than getting the suppliers to potentially try and give us that understanding and that prediction, could we just take all this basic acceleration gyro data, put it into a data lake, maybe the RDG data lake as an example, and get clever analytics people, machine learning, who knows, to start doing the data churning that might give us a bit of a clearer answer as to what's going off with the system and where we see the risks. I don't know, lots of things to consider there. But I think one of the main sort of factors in doing this work as well, away from obviously the issues that were mentioned earlier on, is the fact that Network Rail, or the operators, are asking Network Rail, what data do we want? Because they've got obligations to fit monitoring equipment to fulfill their own franchise agreements. And at the moment, other than things like track geometry or unattended geometry systems, we can't actually answer that question. So we're hoping that this work can get us in a place where we can say, oh yeah, this is exactly what we need to fit, because we can manage the data and this is a risk it's preventing or can help to prevent. And I think, so for us, the sort of next steps within Network Rail then, we're still, this sort of trial was just recently come to an end. So we're cascading the findings and recommendations to the regional leads to see what appetite is for the further work. But a lot of people are interested, but everyone sort of understands the challenges of what I've just mentioned with regard fitting the equipment is relatively the easy part. It's the data management and what do we do with that data and how do we realise that benefit. So we're just having discussions on that. And yeah, we've got our research and development portfolio that's got opportunity to further the research. So if we can get a good enough business case, we can definitely further that work as a phase 2. But I think the main thing for us is how can we effectively land it and realise some benefit from the immediate learning, whilst we then look at sort of the wider potential from in-service monitoring. So yeah, I mean, I didn't realise I could talk about rough rides for so long, but hopefully it gives you a bit of a flavour for what we've done. And yeah, I've not gone into lots and lots of detail because there's a lot of work that's gone in the background. So hopefully it's given you a flavour, and yeah, happy to answer any questions.
Thanks very much, Russell.
No worries.
Thanks for soldiering on despite having quite a nasty cold there.
I know, yeah, my nose is running and all sorts of that, so apologies.
No problem, mate. No problem.
Okay.
Really interesting, and obviously quite a challenging bit of work there, really. So many variables, and obviously rough rides are quite subjective, aren't they, from a driver's reporting perspective?
Yeah, I mean,
definitely.
Something controversial that I wasn't going to say, but I will say it because I think it's pertinent, is when we set our track geometry wavelengths for obviously monitoring or inferring ride quality, it was in the BR days and we had a limited amount of rolling stock types, whereas now we've got a significantly we've got quite a significant variation of rolling stock types. So is this something there that we've not really continued or managed the risk throughout that time? And is it something that when GBR comes, is that something that could be looked at in future? I don't know. Limiting the types of rolling stock so that we can manage it effectively by geometry management process. Don't know.
I thought it was interesting as well how responding by reducing the line speed to kind of 40-50 mile an hour isn't necessarily the right thing to do either, which would probably normally kind of be our response to that sort of issue until we get out there. And
yeah, I mean, in a lot of cases that does work, but yeah, we have got evidence on some sites where, like I said, it's not that clear cut. So
yeah,
we'll
definitely. Chair's privilege. I'll get the first question. You mentioned You mentioned that, obviously on the continent they're fitting a lot of this type of monitoring. Are they any further along in terms of like their prediction rates and utilization of the data?
So yeah, it's a good question. I think although they're further along with regard the sort of instrumentation fitment, they're using it for different purposes. So they manage rough rides completely different to us. So when I said what's the issue for us, we'll send a team out, we'll stop traffic. So the performance impact is quite significant. What they do in the continent is they basically bring in the acceleration data, and they've got sort of force measuring wheel sets on some vehicles, and they pull all the data together and basically build a risk profile. So if they've got a geometry issue and a high acceleration and potentially something in the wheel force, they will use that as and basically send the team out as a high priority to that site. But yeah, the rough rides element, they just manage it via geometry, and essentially, yeah, it does happen, but they don't manage it the same way we do. So not a lot to learn in that sense.
Fair enough. I've got a few questions dropping into I think they're questions. Justin, thanks for the presentation. A lot of work has been done from his days traveling the network with the analog black box, marking mileposts with the spotter's window. Again, so many variables. A question from Jose, it looks like. For S&C entry jerk and lateral acceleration, is there any experience available in relationship between dynamic measurements and the calculated kinematic values? Some publications refer to old experiments where dynamic measurements are at least double the calculated static values.
Yeah, it's a good question. It's not something we've looked at directly, but it is a good question. It's something that I think, again, as part of that further work I mentioned, we ought to consider. So one thing that we have identified as part of the work is that due to the sort of subjectiveness of the reports, typically if you're on, going over a structure, so a bridge structure, for example, coming off that onto ballasted track, or going over S&C, there's always like a change in stiffness or a change in that ride or perceived ride. So drivers don't typically report things at those locations. It's only on plain line sections. So you can get the same response or even worse response over things like S&C and structures that won't get a rough ride report. But that doesn't mean that the vehicle response is any less bad, if you like. So definitely something to consider. It's a good question.
Yeah, definitely. Got one from Thomas. As the data identified vehicle characteristics, such as unsprung mass, that will affect the measured ride quality?
Yeah, again, another good question. Something that we really want to understand is not just not just unsprung mass. I'll come on to that in a minute, but like the mass and the mass sort of or loading condition of the vehicle. So, some of the newer rolling stock types, we can understand, how many passengers are on the vehicle and where that load distribution is. So that's one thing that we don't know from the tests that we've done that will have an influence and an impact. Well, yeah, the unsprung mass side, there's again a lot. I think when we simulate things in like Vampire, for example, it's really good at telling us what the vehicle's doing, but you can't put any changes in, like, throughout that simulation. So you can't see what the effects are with a slight variation. So I think, maybe that's something that we could draw from the acceleration side, where we've got equipment fitted to the axle end, for example, and obviously the bogie, to see if there's obvious differences. But some work that we did do looked at effectively you can start to remove the effects of the unsprung, or understand the effects of the unsprung mass just from the frequency of like acceleration. So over a certain frequency, it correlates quite well with what you'd expect from basic masses force acceleration. So something to look at.
Right. And if anyone else has got any more questions, feel free to come off mute and address Russell directly if it's easier than kind of typing it up. You've obviously covered all bases. You've obviously
everyone's thought, oh, this is dead easy, and realised it's a bit of a nightmare, like we did when we got involved.
Yeah, no, it is. It clearly is. If that's it. Oh, hold on. No, just people thanking you for a great presentation. So if that's all, we can thank Russell in the usual manner with a virtual round of applause, if you want. There you go. A few little virtual hands.
Maybe put everyone to sleep with talking about quasi-static acceleration and stuff.
It's not your usual sort of Thursday lunchtime topic, is it really?
Different,
But
isn't it?